Let us resume Chapter 9. The next topic is Section 9.2, Inferences about the binomial probability distribution. More precisely speaking, what we do here is the normal approximation of binomial proportions. In Chapter 5, and then followed by Chapter 6, we went through some binomial distribution and its normal approximation. But at the time, we focused upon binomial sums. Here, we do binomial proportions. What's the difference? This table, Table 9.1, summarizes it. Suppose that we roll a die, say 600 times. We simply count the number of aces we have. That's what we used to do in Chapter 5. Divide by the number of rolls we have, we get the proportion. That's what we do now. How about the mean or expected value? Well, if we roll a die 600 times and the probability to get an ace is 1/6, so what's the expected value? 100. 600 times 1/6. That's what we used to do in Chapter 5 when we dealt with binomial sum. Now divide by n and we get the original probability again, 1/6. That's a binomial proportion. Standard deviation goes pretty much the same way, square root of npq versus square root of pq over n after dividing by n. It is possible to mathematically deduce the standard deviation formulae, but this is 1000 level stat course, so we won't do that. Just regard these as formulae that you have to memorize. One for binomial sum and one for binomial proportion. Of course, in Chapter 9, we're going to focus upon proportion. Now, how do we use these kind of things? In inferential statistics, let's go ahead with some examples. By the way, here is the summary. Binomial proportion can be approximated by a normal distribution with mean equals the proportion or the probability, and standard error is p times 1 minus p over n, square root of p times 1 minus p over n, or if you prefer this form, square root of pq over n, where q is the same as 1 minus p. Okay, let's go with the most elementary example, confidence interval problem. In a poll conducted by Harris Interactive of 1,179 video gaming US youngsters, 8.5% displayed behavioral signs that may indicate addiction. Find 95% confidence interval associated to this poll. Well, this is confidence interval problem, and the best point prediction is, of course, the poll result, 8.5%. So that goes right in the middle in a normal picture, kind of like this. Like this, right in the middle, 8.5%. And 95% in the middle, which is represented in blue in this picture. And consequently 2.5% to the left, and then another 2.5% to the right. Now, how do we find out the confidence interval? Well, pretty much the same thing we did in Chapter 8, as a matter of fact. Let's look up the normal table and find out the z-score associated to 2.5%, 0.025. We're going to get something like this. Here's the normal table, and here we go. 0.025 appears for z-score of negative 1.96. By the symmetry, positive 1.96 is also automatically another z-score, the other z-score, because of the symmetry. One for the left and one for the right. And consequently, we end up with this equation here. Z-score, which is n minus center over standard error, is equal to plus or minus 1.96. Now, what is the center? 0.085, 8.5%. And what about the denominator, standard error? Well, we have to calculate it using the binomial formula. Square root of n, p over n. Run your calculator and you're going to get this number, and that number goes to denominator. That results in this equation. And that's how you can find out the left-hand side endpoint here and the right-hand side endpoint here. The result is this confidence interval. Roughly speaking, between 6.9% to 10.1%. Let's go to the next problem. Fill in the blank. No less than certain percentage of youngsters show the sign of game addiction with the 99% of confidence level. This problem is a little bit disguised, but no less than blah blah blah, this part is telling us that we are looking for one-sided confidence interval, and more precisely speaking, lower confidence bound. No less than means greater than or equal to something, so it's going to be lower confidence bound. Anything greater than that will be okay. So we draw a normal picture around 0.085 as before. However, not the symmetric shading, but shading only on the left-hand side. 99% not just in the middle, but all the way to the right. And 1% only in the left-hand side. So what do? We look up the z-table associated to 1%, 0.01, and that's going to be your z-score. Let's go back to the normal table. How about 1%? Where is it? 1%. Well, this is the closest to 1%, 0.0099. So it's going to be about negative 2.33. So that's your z-score, negative 2.33. And consequently, we end up with this equation over here. N minus center over standard error is about negative 2.33. As a matter of fact, here in this notebook, I use a little bit more accurate figure. Instead of negative 2.33, I use negative 2.326, which is a little bit better. The same computation follows, as a matter of fact. Center is 0.085 as before, and the standard error, same formula applies. Square root of n, p over n. Solving this equation, we get the lower confidence bound, and after this computation, you can get about 6.61%. That's going to be the lower confidence bound. That is no less than 6.61% of the youngsters show the signs of game addiction. By the way, what if we use negative 2.33 instead of slightly more accurate figure over here? Well, let's run it, and what do you get? 0.0660757, well, still 6.61% if we take appropriate rounding. So this is okay. Negative 2.33 will be perfectly fine as far as I'm grading. I cannot say the same when WebAssign is grading, so you have to be a little bit careful about machine grader, and that kind of thing corresponds more toward a bug rather than the precision, as a matter of fact. I mean, no textbook writer intentionally deviates away from the normal table or any kind of stat table provided in textbook, but sometimes that happens in machine grading, so be careful about those kind of things. Okay, let's go over to the next example, which is a little bit harder because this is going to be a backward problem. Okay, here we go. A political research team is preparing for an opinion poll of an upcoming referendum. By the way, there is a typo. Okay, sorry about that. A political research team is preparing for an opinion poll for an upcoming referendum through a simple random testing. If they want to obtain the point estimate of the referendum within the margin of error of 2.0 percentage point with a confidence level of 97%, what is the minimum number of the sample size? Well, this time we have to find out n value, and n value is associated to the standard error. So what we need to do is to identify the standard error. But there's going to be a bit of a problem. Even after identifying the standard error, we have we have two characters to consider. We have to find out n, but what is p? That's going to be a problem. So what we do in this kind of problem, we have to find out the p-value that will give you the maximum, the biggest standard error, so that we get biggest spread possible for given n value. And that p-value is half, 0.5. So in this formula, we use 0.5 in place of p. That's the standard trick for sample size problem. Basically, we are doing something like this. So z-score is n minus center over standard error, isn't it? And that's going to be approximately equal to plus or minus of a certain z-score, which we will look up. This z-score will be associated to 97%. 97% in the middle, which means 1.5% to the left and then 1.5% to the right. Now, how about n minus center? As a matter of fact, I better show you a picture. Well, okay, here we go. Okay, here we go. We don't know this x bar value or observed proportion, but we do want margin of error as 0.2 this way and 0.2 the other way. One to the right and one to the left. Now, if we take this end, n minus center will be positive 0.02. If we take this end, left hand side, n minus center will be negative 0.02. So the numerator is gonna be, the numerator is gonna be plus or minus 0.02 because we want 2% over standard error. We're going to end up with this kind of equation here. Let me increase the font a little bit further. This kind of equation. Consequently, in the end, plus or minus, this one and that one will cancel each other, and we will be able to identify what is the standard error. With that standard error, we will identify n. Okay, that's the strategy. There's a roadmap, and here we go. N minus center over standard error is plus or minus 2.17. Well, I'm going to leave this normal table to you. For 97% in the middle, 1.5% for left hand side and 1.5% for right hand side. If you look up, you're going to get plus or minus 2.17. But as we said early on, n minus center is plus or minus 2%, 0.20. So canceling out canceling out plus or minus, we end up with this equation without this plus minus thingy, and we get standard error is about, well, after this computation, we get something like this. Now, standard error will be replaced by this one. Remember, we're going to take p as 0.5 because that will maximize the standard error. So square root of 0.5 times another 0.5 over n is approximately equal to, well, the number you got before, 0.02 over 2.17. From this equation, square both sides, solve for n, and then you get something like this, 2,900 something. So approximately 3,000 people will do as for this kind of preparation for polling. Okay, do we have enough time for hypothesis testing? Looks like we won't. So we're going to talk about hypothesis testing in the next segment of video.